morning students, this is Dr. V. Srinivasarao, Assistant Professor of Physics, GDC Uppal. So, today we will discuss about the thermodynamic potentials. So, in this thermodynamic potentials, what are thermodynamic potential, how these are important. So, in this we will discuss about that here, what is first law of thermodynamics. So, here before discussing the thermodynamic potentials, you need to know about that what is first law of thermodynamics and similarly what is second law of thermodynamics. Let us discuss about that what is the thermodynamics. So, thermodynamics is a branch of heat and which we have to study about the heat motion and transformation of heat energy into mechanical work and vice versa. So, many examples are there related to this one. Okay. So, what is the best example in this Carnot cycle? So, we will discuss in future. So, let us discuss about the what is the first law of thermodynamics. So, here the first law of thermodynamics, which is referred to as the law of conservation of energy and which is a fundamental principle in physics and thermodynamics, and also it states that energy cannot be created nor destroyed in isolated system. So, in other way we have to say that the total amount of energy in a closed system remains constant. Okay. So, energy can be which can be converted into one form into another form. So, such as a form of heat to work or vice versa, but the total energy within the system remains unchanged. So, here mathematically we have to say about that what is first law of thermodynamics. So, the first law of thermodynamics which can be expressed here delta U equals to Q minus U, Q minus W. So, what is delta U? Delta U is the change of internal energy of the system. Okay. So, here that is going to be representing here final internal energy minus initial internal energy. That means, you need to say that here UF minus UI, which is nothing but a change in internal energy of the system. So, what is Q here? So, Q is the heat added to the system here. Okay. And where W, so where there is a Q, heat is there, energy is there, and here internal energy delta U, which is going to be representing here delta equals to Q minus W, means Q which is a heat. So, here something which the energy is there means some work has to be done by the system or done on the system here. Okay. W equals to work done by the system. So, this equation which is going to be here writing here dq, that means here there is a change, dq equals to du plus dw. So, the above equation which may be writing here delta equals to q minus w, which is going to be writing is dq equals to du plus dw, or else you can write it down that here internal energy, change in the internal energy du equals to dq minus dw. So, this is the first law of thermodynamics. Okay. So, from that first law of thermodynamics we have been derived the equation, that is how the change of internal energy which is to be writing here, that is d equals to dq minus dw. Next, second one is the second law of thermodynamics. So, which is related to the entropy. Okay. So, what is entropy here? So, the entropy which is to be saying here is which is a physical quantity which is unchanged in adiabatic system. Okay. So, adiabatic system, that means the energy which cannot be flow from the system to the surroundings or surrounding to the system, that is related to the adiabatic. So, what do you mean by isothermal? Isothermal means here the energy which can flows from the system to the surroundings and surrounding to the system here. So, let us discuss about that here in the second law of thermodynamics. The main focus is that entropy here. So, so many here statements which are given by the second law of thermodynamics. So, first of all, you need to know about that here. What is second law of thermodynamics? The second law of thermodynamics, which is a fundamental principle in thermodynamics and which can describe the direction of natural process and the concept of entropy. So, it has a several formulation, but they all revolve around the idea that certain spontaneous processes are irreversible, okay, not reversible, irreversible, okay. That means a process which cannot be acquired in the other direction, that means that is irreversible and lead to increase in the overall disorder or randomness of a closed system, okay. Closed system means initial to final and final to the initial. So, this concept is often summarized as the increase of entropy. So, there are several statements, just now we discussed about that here. What are the statements which was given by the scientist, so related to the second law of thermodynamics. So, let us discuss that. First is the Clausius statement, okay. Heat cannot spontaneously flow from a colder body to a hotter body, okay. Heat cannot be spontaneously flow from a colder body to a hotter body, okay. Is it possible? No. So, here the heat cannot be flow from colder to the hot body, but the heat can flow from the hot to the cold. So, that was given by the here Clausius statement. Next one is the Kelvin-Planck statement. So, what is that statement here? It is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work, okay. It is impossible for any device that which can operate on a cycle. Cycle means initial to final and final to initial. So, which is to receive heat from a single reservoir and produce a net amount of work. Next, third one is the entropy statement. So, here the entropy of a isolated system, single system, never decreases. It either remains constant in reversible process or increase in an irreversible process, okay. So, mathematically here for a reversible process based on the Carnot's theorem. So, here you need to say that dq equals to TdS, okay, or else ds equals to dq by t, okay. ds is the change in the entropy. So, T is the temperature, dq is the change in the heat process. So, here if P is the, P represents the pressure and V represents the volume of the system here. Therefore, the work done on the system here, which is to be says that here dW equals to PdV. So, what is dV? dV is Vf minus Vi. So, here dW equals to PdV. Substitute equation 2 and 3 in equation 1. So, what is that equation 1? D equals to du minus dW. So, on that equation, if you are going to be substituting these two values, dq equals to TdS as well as the dW equals to PdV, you will get the fourth equation, that is d equals to TdS minus PdV. So, this equation called as Clausius differential relation. This equation applies to the closed system performing PV work only, okay. Next one. So, what are the thermodynamic potentials? So, these are very, very important here. So, what is thermodynamic state of a system? Which can be defined as by the four variables named as pressure P, volume V, temperature T and entropy S, which are also called as these thermodynamic potential P, V, T, S, pressure, volume, temperature and entropy, which are also called as natural variables. So, what is the relation between these four variables, which can be obtained by first and second law of thermodynamics, okay. D equals to dq minus dW and dq equals to TdS. So, what is the state functions that along with the corresponding equations of the state describes the equilibrium behavior of the system as a function of natural variables. So, PV, Ts, which are called as thermodynamic potentials. So, 4 thermodynamic potentials. What are the 4 thermodynamic potentials? Which are the internal energy U, Helmholtz function F, and enthalpy or total heat function H, and Gibbs function. Okay. So, you need to know about that what is internal energy. So, internal energy, which is to be represented here U here, which is the total energy contained within a system, including both kinetic energy as well as the potential energy. Okay. So, it is a function of temperature T, volume V, and the number of particles, and the change in the internal energy which can be related to heat transfer and work done on or done by the system, work done on the system or work done by the system. Okay. Next one is the enthalpy H. Enthalpy is the sum of the internal energies and the product of pressure and volume. It is often used in analyzing processes at a constant pressure P and providing insights to heat transfer under these conditions. Okay. Next one is the Helmholtz free energy, that is H. The Helmholtz free energy, which is defined as the difference between the internal energy of a system and the product of its temperature and entropy. So, we in detail we need to discuss with respect to equation part. Okay. Just you need to know about what are the definitions of these. Okay. After knowing the definitions, we should write it down with respect to the equations. So, here it is what is that Helmholtz free energy, which is a particularly useful for a system at a constant temperature, okay, and volume, and which helps predict whether a process is occur spontaneously or not. Okay. Next one is the Gibbs free energy, G. So, here the Gibbs free energy, which is the difference between the enthalpy and the product of temperature and entropy. So, it is used to analyze the system. What is the use of this Gibbs free energy? So, which is used to analyze the system at a constant temperature and pressure, and which can helps to determine whether a process is thermodynamically favorable or spontaneous. Okay. So, these are the definitions. Next, there are two energy functions which have been used so far. What is that first one? Internal energy, enthalpy. Okay. Internal energy is U. So, here enthalpy is H. Above definitions, how you are going to write down with respect to equations, that is very, very important. So, from the first law, we know that dq equals to du plus dw. Okay. So, what is dq? From the second law, which is to be representing here dq equals to TdS. So, that is to be writing here from first law. In place of dq, substituting the second law, dq equals to TdS. So, the first law become here TdS equals to du plus dw. In place of dw, what is dw? PdV. Okay. Work done on the system or done by the system here. So, here internal energy d equals to TdS minus PdV. So, here the internal energy, which is a function of entropy S and volume V, and next one is the enthalpy. Enthalpy H equals to U plus PV. Okay. U is the internal energy plus work done. So, that here by differentiating this equation, dH equals to TdS plus VdP. Okay. TdS plus VdP plus PdV. So, that here at a constant volume means here there is a 0 that will comes here. So, that from above conditions, if you are going to be substituting by simplifying this equation, enthalpy dH equals to TdS plus VdP. So, H is a function of S entropy and pressure P. Next, Helmholtz function. Third one is the Helmholtz function, that is F equals to U minus Ts. Again, another one is the Gibbs function. So, G equals to U minus Ts plus PV. So, by substituting these conditions, G equals to H minus Ts as well as the G equals to Gibbs function G equals to F plus PV. So, what are the properties of these? So, by considering here Helmholtz function here F equals to U minus Ts, by differentiating here dF equals to du minus Tds minus sdt. So, from the first law here du equals to Tds minus Pdv and dF equals to minus Pdv minus sdt. So, F is a function of V comma T. V is the volume and T is the temperature. Gibbs function G equals to U minus Ts plus Pv. So, by differentiating this equation, you need to get the dg value equals to U minus U method Tds minus sdt plus again if you are going to be differentiating here, you can able to see that here Pdv plus Vdp. So, from the first law of thermodynamics, d equals to Tds minus Pdv. So, from that above equations, by substituting here, what you will get here? So, minus Pdv and plus Pdv will get cancelled as well as the minus Tds and plus Tds, which is also going to be cancelled here. So, finally, the equation which comes here dg equals to minus sdt plus Vdp. So, where Gibbs function G is a function of here temperature and pressure. Okay. So, by denoting these equations, and let us consider that the internal energy du equals to Tds minus Pdv, where internal energy which is a function of entropy and here volume. So, partial differentiation, how we are going to be writing here d equals to dou u by dou s of V into ds plus dou u by dou V of s into dV. So, let us consider that dou u by dou s of V is a temperature T and here pressure P which is equals to minus dou u by dou V of S. And similarly, enthalpy equation, considering the enthalpy equation dH equals to Tds plus Vdp, where enthalpy H is a function of entropy and pressure. Again, from the above process here, by considering or doing the partial differentiation here, dH equals to dou H by dou S of P into ds plus dou H by dou P of S into dP. Let us consider that dou H by dou S of P which is a temperature T, and how we are going to be writing here this equation means here from the second law of thermodynamics as well as the entropy equations. So, we are writing here, and also V here dou H by dou P of S. Next, Helmholtz function dF equals to minus Pdv minus sdt. F is a function of volume and temperature. So, again by doing the partial differentiation, dF equals to dou F by dou V of T into dV plus dou F by dou T of V into dt. So, in the above equation, same process which we have been discussed in that. So, that is the pressure P equals to minus dou F by dou V of T and entropy S equals to dou F by dou T of V here. So, what is the Gibbs function here? dg equals to minus sdt plus Vdp. So, where Gibbs function G is which is a function of temperature T and pressure P. So, dg should be equals to here partial differentiation dou G by dou T of pressure P into dt plus dou G by dou P of T into dP. And entropy in the above equation S can be here replaced by here minus dou G by dou T of P, and V can be replaced here dou G by dou P of T. Okay. So, all the four equations, what are the four equations here? Internal energy D equals to Tds minus Pdv, which is a function of entropy and volume, and dH equals to Tds plus Vdp, which is also function of entropy and pressure, and dF equals to minus Pdv minus sdt. F is a function of V comma T, V means volume and T is a temperature, and dg equals to minus sdt plus Vdp, where G is a function of T and temperature T and pressure P. So, by using these equations here, what are the Maxwell's relations here? So, here in this Maxwell's relations, so temperature, volume, pressure and entropy, only considering these four variables here with respect to entropy, volume, temperature and pressure, how these equations are going to be writing a differential form. So, that is the here dou T by dou V of entropy S equals to minus of dou P by dou S of V. So, this is the first equation, okay. And second equation is that here dou T by dou P of S equals to dou V by dou S of pressure P, and third one dou S by dou V of T equals to dou P by dou T of V, and finally here minus dou S by dou P of T equals to dou V by dou T of P, okay. So, here how these equations which are going to be deriving here. So, from the above discussed, what are those here? From the first law of thermodynamics as well as the second law of thermodynamics, okay. So, from that here the internal energy du value and also Helmholtz function, okay, and Gibbs function, okay, dg, df and du. So, by considering all these four equations, so by choosing that here any of the four, that means PVTS, pressure, volume, temperature and entropy, all these any of two by considering, so which is a function, so that we need to write it by the form of here a differential, partial differential equations, so that we can derive these equations easily, okay. So, what is the simplest method to derive these equations? We will discuss in coming classes, but you need to remember that here these basic four equations, Maxwell's thermodynamic equations, so that here this is very important for examination point of view. You need to know that how these equations are going to be deriving from the above said four equations, okay. So, here temperature, volume, pressure and entropy, okay. So, you need to know that here. So, these are the four equations. So, from these four equations how these are going to be here correlating with each other here, okay. So, we will discuss internal energy differential form here d equals to TdS minus PdV. So, which is a function of u, which is a function of entropy S and volume V. So, the differential form equation here d equals to dou u by dou S of V into ds plus dou u by dou V of ds into dV. So, here we are to be representing here a temperature T as well as the pressure P. How this equation which comes here? So, I will show you one example, that means here for partial differential equation how we are going to be doing here, that is to be here. After that you can prepare for here Gibbs function, Helmholtz, okay. So, today we will discuss about that here how this equation partial differentiation can be done. So, here Clausius differential relation which can be interpreted here to get this equation, total differential equation dE for the represented function here. So, that is here which is a function of entropy S as well as the V here. So, you need not to be worried about that here whether it is in slide one form is there, in here in textbook that is different than that. So, you need not to be worried about that, okay. So, here E equals to E of SV which is a function of S and V, okay, entropy and volume V. So, by differentiating here dE equals to, so what is the partial differentiation here with respect to entropy as well as the volume here, dE by ds of T into ds plus dE by dV of S into dV. So, comparing with this above equation, So, with that Clausius differential relation here. So, what is that equation? d equals to TdS minus PdV. That means here dE, which is nothing but a du, you need not to be worried, internal energy. Okay. So, d equals to TdS minus PdV. So, we are to be writing here with respect to this here, that is du by ds of T, which is equals to temperature T equals to, we are to be denoting here capital T temperature, as well as the here dE by dV of entropy S equals to here minus P. Okay. You do not be worry here, whatever the letters which are to be representing info with respect to here internal energy, that is whether it is E, U or E, whatever it may be here. Okay. So, here by continuation we are to be writing here what is enthalpy. Enthalpy H equals to here, which is a system and which is a function of here entropy S as well as the pressure P. So, how you are going to be writing here? So, H is a function of here S and P. So, you know that here what is that equation here, U plus PV or E plus PV, do not be confused here. So, since H is a function of enthalpy, H is a function of H of S comma P, entropy as well as the pressure P. So, by doing the partial differentiation, dH equals to, be careful with this. So, we are to be giving here two examples here, one is that here internal energy, another one is that here enthalpy H. So, you can get an idea how to derive this partial differential equations from the above said 4 equations. Okay. From the first law of thermodynamics we already derived that, and second law, okay, dq equals to TdS. From both these equations we are to be deriving here, okay, what is the dH value, what is the du value, what is the dF value as well as the dg value, Gibbs function value. So, I am showing that here only two, for one is that internal energy, another one is that here enthalpy. So, how these partial differential equations has been derived. So, here enthalpy H equals to, which is a function of entropy as well as the here pressure P. So, partial differentiation dH equals to dH by ds of P into ds plus dH by dP of S into dP. Why? Because of which is a function of entropy as well as the pressure P. So, also you know that here H equals to E plus PV. Okay. So, by doing this differentiation, H equals to U plus PV or E plus PV, whatever it may be here. Okay. dH equals to here PdV as well as the VdP. So, by the above equation H equals to E plus PV, we have to write down that dH equals to dE plus PdV plus VdP. So, by substituting in this equation, which one? This equation dH equals to dE plus PdV plus VdP, in that by substituting the equation, you can get here dE value equals to du minus PdV. Okay. So, here you have to get the equation here dH equals to TdS minus PdV plus PdV plus VdP. So, that what will be cancelled here? Minus PdV as well as the plus PdV get cancelled. The remaining portion will be dH equals to TdS plus VdP. So, this is the equation here. So, from this equation here, yes, we have been writing here dH equals to TdS plus VdP. How do you get this equation? So, by doing all these and by substituting first and second law of thermodynamics, you will get this equation. By comparing with that equation here, so you will writing here dou H by or dH by dou P dP of P, which is equals to temperature T, as well as the dH by dP of S equals to V here. So, you can get an idea that here how to get these equations. Okay, right. Thank you.